student I've had from New Mexico this whole year. Go back and check my notes. So Max worked with me on this schistosomiasis. So as some of you know, in my Organic 2 class, we have students sort of make a very long list of compounds, and at the end of the year, I had a big pile of stuff, and I said, Max, take care of this. And to his credit, he did a good job of trying to interpret what I meant by that, and then trying to extend the project in what I think is a really interesting way to look at a little bit of organometallic medicinal chemistry, which is very cool. Right now, Max is looking for work to try and apply his prodigious skill set in any number of directions, which is very exciting. And so he'll be, I'm sure, happy to answer questions not only about the synthesis that he's going to talk about, but some of the medicinal chemistry issues, some of the schistosomiasis issues. It's all very cool. So, good for you.
Awesome. Hey everybody, my name is Max, and I'm doing my presentation on anti-schistosoma drug synthesis. So that's a really long word, so we're going to break it down at the very beginning. This is Schistosoma mansoni. It's a type of blood fluke, commonly found in Africa. There are many different types of schistosoma, but this is the one that we're going to focus on here today because it's the most prevalent. And you can see that you have a bunch of different kinds, and this two shown up here. So you have this one right here, which is the schistosoma, and then these are the blood fluke when they're in the host. So you can find schistosomiasis pretty much in hot areas and developing countries where you don't really have clean water to bathe in or things like that. And it's really a big problem because there are 200,000 people that die of schistosoma-related illness every year. 200 million are at risk for schistosomiasis. So the life cycle of the schistosoma, we're going to start down here at the eggs because that seems like a good place to start. So we have the eggs down at the bottom where they're in the water, and they can make it, they develop enough to where they can infect snails, and they gestate in the snails until they become this little thing with this tail. Looks kind of like a hook, and there's a reason for that because it will hook into the skin of mammals and then go into the blood where it loses the tail and then matures in the liver into these two worms. And you can see that these two worms, there's the male, which is basically the pea pod, and then there's the female, which is like pea right in the middle of it. So it kind of fits right in the middle of it like a hot dog. And then in there in the liver, it lays eggs, which are then transferred to the bowel and the bladder, and then released back into the water. So symptoms of schistosomiasis, it seems very similar to like a common cold, right? So you have rash, fever, chills, cough, and muscle ache. So without knowing what this was, you would just think you were coming down with something. But it gets a little bit worse when you have schistosomiasis in children, where they can develop anemia, malnutrition, and learning disabilities. This is mostly from the nutrients that would be going to like development as a young child, going to the schistosoma instead. And then in extreme cases, when the eggs are laid, they can travel through the bloodstream and get into spinal fluid and like your brain. So it causes problems like seizures and paralysis, which can lead to death. And it's worth noting that all of the symptoms that you get from this are not from the worms themselves, they are developed from the eggs. It's your body reacting to the eggs being released. So methods of attacking the disease, like I said, this is a freshwater disease. After it leaves the snails, it sits in the water. So if we were able to treat the water, that would solve a lot of problems, but there's not a lot of infrastructure that we can do this with, and that's where a big problem is, especially in developing countries, where we can't just filter this out before people shower or bathe in it. So we're going to focus on treating people that do catch this disease. We're going to use drugs to do that. So the current drug right now is praziquantel. It is a deworming drug. You can see it a lot on the market. It's pretty much, it is the only drug being used right now. And it's causing a lot of problems because we need more than one way to solve this, especially with immunity coming along. You can see it in the United States in packages that look like this. And if you notice at the bottom it says, warning, keep out of reach of children, they're not for human use. That's because it's not used in the United States for humans. It's used for animals, and if you have like your dog, they say, oh, your dog has worms, they're going to give your dog this drug. And we need to try and develop something that could be used other than, something that's veterinary medicine. So, what praziquantel does, it can cause blebbing in the cells of the worms, and blebbing is the only word that I know that actually sounds like what it describes. And here you have a normal cell And here you have a cell with a bunch of little blebs on it. They look like a skin tag if you've ever seen one like a dog or something like that. Here's what blebbing looks like on the schistosoma. You can see where B is pointing to. Those are the blebs that are coming out, and those are not supposed to be there. VS is the ventral sucker. That is where it attaches to your body. And S is a little gross, is where the skin is starting to fall off the worm because it is dying. So it's sheathing off. So how praziquantel works. It causes an influx of calcium in the bloodstream, or in the body of the worm, which can eventually lead to paralysis. And it does this because when calcium is released into the muscles here, it opens up active sites on the actin filament, which is this right here. And those active sites can be grabbed by the myosin right here. So when you have a lot of calcium in your blood, it's like getting a cramp. So it just tenses up and tenses up and tenses up, and it doesn't release because there's too much calcium in the blood to leave and then not come back to the active site, or not come back to the actin. So resistance is becoming a problem. Praziquantel only cures 80 to 90% of people taking it. So that's not great. You would hope that you could have a drug that could just get rid of all of it every time. That's ideal. But this doesn't do that yet. It also doesn't work on all parts of the life cycle. So it only works on the mature worms. So when they're in that pea pod hot dog form, that's the only part where this is actually going to work. And then lastly, you must have a positive diagnosis. And the only way you're going to get a diagnosis is if the body's already having an immune response to the eggs, which means you're at the last stage, it's already in the worm form, so you can't treat it before then, because you won't know it's there. In these pictures, you can actually see a resistance developing. Both of these were treated with praziquantel. The one on the left its lineage had seen praziquantel before, and the one on the right had. And as you can see, the one on the left over here is very constricted. It looks like it's heavily affected by something, as to where the one on the right could be alive. It looks like it could be alive, but it's not. It's dead. But it's not as constricted as the other one. So where does treatment work? Like I said, we have to be able to treat it in the human body, so that leaves out all of this. You can't just spray drugs into ponds or like fresh water anywhere. Like that's going to cause a lot of problems.
You should.
You could. You should not. Next, we can't treat it here because praziquantel doesn't actually work on this stage, number one. And number two, we don't know if you have it at this point. Like if you just had this in your body, we would have no idea other than, no, you would have no idea. So this leaves us with a few options. We can treat it in the water, and that would be through water treatment. We could try and grab the eggs or make the eggs not work, but that wouldn't solve the overall problem. So we're going to focus on treating it here at the adult worms. So what that means is that there's really a very brief window where we can try and get these drugs to work. So synthesis goals. So we're trying to make an anti-schistosomal compound, just anything that has shown activity against schistosoma. Sorry, it's a long word. Anything that shows activity against schistosoma is what we're looking for. We want something that kills the schistosoma instead of just paralyzing it, because praziquantel just paralyzes it and then the worm falls out and then it's gone, hopefully. But we want it to be dead. Like, we don't want these anymore, ever. And lastly, have fun. I mean, most of this was me this summer trying to make drugs that looked cool, so that's always pretty fun too. So, finding a starting molecule for making these drugs. There are so many different drug-like compounds that exist. So there's 10 to the 60 possibilities. That is a massive number. Just for an example, if you put a drug-like compound on a piece of paper and then stacked all the drug-like compounds on a piece of paper up in the air, it would be 10 to the 53 kilometers, which is still a big number, so I'm going to try and break it down a little bit more. The nearest galaxy is 10 to the 19 kilometers away. That is roughly 2 light years. So you could reach the nearest galaxy roughly 2.5 times with paper, with 1 molecule per piece. So any of these could have some sort of reaction with schistosomiasis. It could help, but we have no idea where we're going to start in that massive stack of paper. Good thing we didn't really have to rely on that because someone else did this job for us. They used previously known anti-malarial compounds to test against schistosomiasis as well. Malaria is also a well-known parasite. I'm pretty sure most of you guys have heard of it. I hope so. They used these known drugs that had anti-malarial activity in them. You can see that most of these drugs have these aryl rings, which basically means you can push the charge around the molecule. They've got some flappier aryl rings, I guess, ones that can kind of move around a little bit more. So we focused on this one right here. It's symmetrical, which I'll get into later why that's a good thing. And it's pretty easy to break down and separate into something that we can mess with. So from the paper, we're going to develop our ideology. We want to have this known base right here. This is our starting point. This is our quinoxalin. This is basically the bottom of the Lego tower that you're going to start stacking stuff on top of. So we have this known base. We're going to have a hydrogen bond donor here. We do try and replace it with a hydrogen bond acceptor later on. But something that links this compound, or this aromatic ring system with an aromatic ring system down here. We're going to have another aromatic ring, and then in some cases we're going to put a halogen in there, which is basically, if you look on the periodic table over there, it's fluorine, chlorine, bromine, iodine, and AT, which I made up. It's fake. So from there, we have our base, right? So how we're going to think about this is we have these two R groups. We can add anything on there that we want. So we're going to start with some stuff that we know or we think should work that looks pretty similar to what we saw on that last slide, where Q equals that base. We're just going to try and attach those ring systems on there. But we're also going to try and find something that maybe we just haven't tested yet. We don't know if it works. We're going to have some new, funkier looking stuff like this ring system up here. Maybe we're going to ignore the aromaticity. Maybe we'll just do it like a chain. So we have a lot of things we can choose from. So that's kind of where I came into this project. Oh, yeah, so we can we can mix and match any of these we want. We could put this one right here, maybe that one right there if we wanted to. If we got really antsy and we were running out of things to make, but that was never a problem. So finding the drug to screen for. So I started looking back at antimalarial compounds, and there's a known antimalarial compound called Ferroquin. This is what it looks like, or this is the paper I saw that used this compound. That is not actually what it looks like. That is a terrible drawing. Even though it looks really cool, it looks a little bit like a flower, and I was like, I want to make the flower molecule. This is what it's supposed to look like when drawn properly. So you notice that there's a very weird group in here, and if any of you guys have taken orgo, you can see that this is not something that we deal with very often, especially since it is a metal center, and we don't use metal in organic chemistry all that much until you get to advanced organic, which is the only thing you see. So this is ferrocene. Ferrocene is basically an ice cream sandwich where you got carbon as the bread on the sides, and you got a nice, delicious iron center in the middle that's actually bonded to every carbon on both of those rings. Very, very strong or sturdy. It doesn't really fall apart once you have it there, so it's a good starting point for us to figure this out with, and it has antimalarial compounds from the Ferroquin that we saw before. So to try and add these onto the molecule, we have to think of something called a retrosynthesis. It's basically where we have our molecule, and we want to break it down into manageable pieces until we get to something that we can buy from some distributor, and hopefully for cheap, which we got pretty good, so that was nice. This is what we did. So you can see we have our two goals over here, one with an oxygen linking bridge and one with a nitrogen linking bridge. So we're going to break these down into manageable parts. It seems like an obvious step at the first bit. The weakest part seems to be this little string attached to it right there. So we're going to try and break it down, and we broke it down into this dichloryl quinoxalin, which if you took orgo, you actually use a ton of this stuff. And then we're going to try and break it down even further. With the alcohol species, it's pretty easy. We just broke it down into the aldehyde, which is ferrocenocarboxaldehyde, which is a long word. Didn't wrap around the vial. And our second one, we couldn't just buy this ferrocene carboxylamine, so we had to try and break it down even further. So we broke it down into the oxime, which looks very uncomfortable, with the N and the OH bonded to each other. And then we broke that down even further back into this aldehyde, so we got the same starting point for both of these. So, first steps. We wanted to start with our aldehyde over here, and we did that by exposing it to NaOH, hydroxylamine, and ethanol, and boiled it. And then we reduced that with LiAlH4. I will show you the mechanism in just a second. With the alcohol creation, we just used NaBH4, which is a known anti-Markovnikov. It's basically a primary alcohol creator. Not really necessary in this case, but it worked pretty well. So here's the oxime, that weird thing I pointed out earlier. So you start off with your aldehyde over here, and you use this hydroxylamine, which is a base, and it backsides attacks onto the aldehyde, where you get a molecule that looks like this. That oxygen is not happy. It is super negative, and right next to that N+, you're going to have it grab the hydrogen from that N+, which leaves you with this. And it's still not really psyched about where it is right there, so it's going to grab another one, and it's going to leave as water, giving you this oxime over here. Next, we treat it with LiAlH4, which is a reductant, so it just basically got rid of the OH there, and it got rid of that double bond there, leaving us with our ferrocinocarboxylamine. Next, we have these big molecules that we wanted, so we have the amine group, and we just treated it with a weak base, boiled it in DMSO for a day. It was probably maybe more than that, but a day. And we actually got 2 different products. I didn't really expect this. Steph might have, but we got our target molecule that we were really aiming for. We also got the mono edition, which is pretty cool. Like I said earlier, we could try and mix and match what else we wanted on here. And with this, we could probably do that and make some cool stuff. So, with the next one, we actually had to use a strong base, which is terpbutoxide. We had to do that so we could deprotonate the oxygen over here so that it could actually attack where it needed to. Otherwise, it wasn't going to do anything. And then again, we got the mono and the di addition. And I keep saying that we got this, and I need to explain how we know we got this. So, methods of confirming the molecule, we have a bunch of them. I'm going to talk about 4. The first one being IR, which is infrared spectroscopy. It uses lasers, and lasers are pretty cool. And if you don't believe me on that, because you have no reason to, you can ask Pink Floyd, because they will tell you that lasers are pretty cool. Next, we have melting point, which is exactly what it sounds like. You just melt your substance, and you write down where it melted. Pretty straightforward. We have NMR, which is a big magnet. I will get into why it's a big magnet and what it does later, but that's all you need to know for now. And lastly, we have thin layer chromatography, which is TLC. It helps you detect polarity differences. So if you could separate like something like methanol from hexanes or something like that. So we're going to start off with IR. This is our IR machine. We put our sample in underneath this little claw, crush it down, laser goes through it, comes back, and the machine gets a read from where everything is on there. So what we see when we're using IR is we get this crazy squiggly line that seems to say nothing, but it really doesn't help it break it down. It spots functional groups, and on this molecule we have a big functional group here, we've got an oxygen here that could do something, we have nitrogens here and here. Those are very important functional groups. So the ferrocene functional group you can see at 3213, and that functional group right there you can see at 3079. So we know we got those 2 functional groups. It doesn't say quantity, it doesn't say purity, it just says we have those functional groups. And if I was really good at IR, which I'm not, so this is like in quotations, this group right here, the carbon, oxygen, carbon, can normally be found right in here, and it's a bunch of different peaks. But I'm not good enough to know really what that is. I don't know if this is accurate enough, but it's good to know. So, melting point. So, like I said, it's exactly what we use. We used a device that looked a lot like this. It brings up the temperature in the device to a certain amount, and then it raises a degree a minute. And this is really what we're looking for. We put it in a little glass tube. It's almost like a test tube, but it's a capillary because it's like tiny. And we melt it down, and we start seeing it. It looks like slushy snow, and then it goes clear. And that's when you know you're done. You measure that range, and the tighter the range, the more pure you have it. We can also test that number against known substances. If this molecule has been made before, it should have the same melting point as the literature values. Unfortunately, all of ours were above 200 degrees Celsius, so we didn't actually get any numbers for this. Next, NMR. So NMR is a little more complicated than the rest of these. It detects protons, basically hydrogens that are attached to the molecule, and you can get a result on how these hydrogens interact with one another. And it shows you where they are on the molecule, and it shows you where other withdrawing groups are on the molecule, or other functional groups are on the molecule. It detects each unique proton, which is important to know because not all protons are unique when you have them there, and each unique proton reacts to a certain frequency of the big magnet oscillating, and that's how you get your results. So, what makes a proton unique? Say we have our dichloroquinoxylin, which was one of the starters we used. We have 4 different hydrogens here on the molecule. Only 2 of them are unique. So we have the blue that have the same charge and the red that have the same charge. And that comes from the fact that chlorine and nitrogen up on the periodic table are really electron withdrawing over here on this side of the table. So they're going to try and pull charge from the rest of the molecules on there, meaning that they're going to have kind of like a big Slurpee straw pulling charge down this chain right here. But because it's symmetrical, it's going to pull equally on both sides. So you're not going to see 4 peaks, you're only going to see 2. This gets a little bit more complicated when you bring in something like ferrocene, which looks kind of like a mess, but will help clean it up for you. So if you think about oxygen as your withdrawing group and where it pulls the charge through, you have your red group here, where it's going to pull from the same carbon. You have your blues that are going to be the same charge, the greens. And then because of this big ice cream sandwich thing that we have, it's going to pull all of the charge straight through that ferrocene, or straight through the iron, ferric iron. And all of these H's on the bottom are going to be the same charge. So you can see a big peak there. What this means is if you look at the NMR, which is this is what you see when you pull it up, you're going to see just these big peaks, and we'll break that down too. So these hydrogens on the side over here are going to be that big peak, and these are going to be that big peak. This peak at 0 is a solvent. It is your deuterated solvent where the hydrogens in the solvent don't react with NMR. When you look at ferrocene, it's a little bit more hard to look at. So first we have our small peak over here, which is that red H right next to the oxygen. It's going to be most withdrawn by the aldehyde on the end. Next we have our blue hydrogens, our green hydrogens, and then a big peak for our pink hydrogens because they are all, they're all the same charge, and that's where the height of the peak comes from. There's more of them. So, how do we know what we got? So, biggest thing is we can tell the difference between our mono and our di addition here. If you look at these big peaks, you should see your dichloroquinoxylin or your quinoxylin group there, and up here you'll see that too. And you'll notice that there's a bunch more peaks where that quinoxylin should be, and it's because we no longer have a symmetrical molecule. So each one of these hydrogens over here is going to have a different charge now because it's being messed with differently than it was before. Next, we have our ferrocene peak and our alkene peak right there. And we have them actually stacked on one another, and it's kind of a mess, so we're just going to call that a multiplet because that's a lot of time and effort to go through all of that. So, next, we have TLC. This separates polarity, so if you have a very polar molecule like water or you have a very nonpolar molecule like hexane, those are going to have different polarities. Things that are very polar are going to stick to this silica plate here. Silica is also a really polar molecule. The silica on this plate is very polar. So things that are also polar are going to stick really tightly to it. So when your solvent goes up the plate, the things that are more tightly stuck are going to stay closer to the bottom, and things that are going loosely stuck are going to move to the top. So you have non-polar stuff on the top and very polar stuff down at the bottom. Here you can see a TLC, a really nice TLC of a certain molecule where you can see very good separation. They probably came from the same spot, and the non-polar stuff went way higher than the polar stuff. Okay, so we know that we got our 4 results from these testing methods. We know we got 4 different things. However, purification was tricky. I don't know if you guys saw in the NMR, there was a lot of other peaks that I didn't have labeled, and that's because there was a lot of solvent in there. There was some icky stuff that we don't really know what was in there. So if we really wanted to purify it really well, like a longer column would be good, which is basically your TLC, but it's just in a tube instead. Or just a different solvent that we need to try and purify a little bit better. But it wasn't pure enough to send out to test, which is pretty sad. And but don't worry, we had a bunch of other stuff we could send out as well. Like Stefan said earlier, I was working with the orgo stuff all summer, and basically purified everyone's molecules from earlier in the class, only to find out that we couldn't use a lot of them because the yields were really bad and we had to start over. These are the ones where we started over. Stefan put them in overnight, and then I purified them over the next week. And we actually got a bunch of different molecules that we could send out. We sent them out to Switzerland to test against schistosomiasis. These are all the molecules we sent out. Some of these means Stefan didn't make. There was another lab member that worked on these. But as you can see, we had sent a lot of them out. These are the molecules that actually ended up working pretty well against schistosomiasis, and it's not in a paper yet, so this is just me talking and telling you they looked good. But as you can see, they all have those bases here, the quinoxylin base. They've got some sort of nitrogen here, here, and here. Literally all of them have nitrogen, and then all of them have some sort of alloy on the end, which ferrocene does not, which would be interesting to try and figure that out afterward. They also actually tested these for hookworm too. So we were having a problem where we were using anti-malarial drugs. If they had tested the anti-malarial drugs along with other parasites, this wouldn't be our problem anymore. But, so we learned from our mistakes, so we tested all of these molecules against hookworm, and literally almost all of them had some sort of activity against it, which is really promising, and hopefully will help someone's research along the line. That being said, what is next? So once we find molecules that work, once we find something that is working a lot of the time, 100%, maybe even 90%, we can start to make like a drug cocktail. But we can only do that once we figured out the mechanism of the drug, basically how it affects the schistosoma. We know praziquantel affects it by causing an influx in calcium. And if this did the same thing, we wouldn't really want to put them together because they'd compete with each other and it would cause problems. But if it had a different mechanism of attacking the schistosoma, that would be fantastic, and that would be a positive idea for a drug cocktail. And we also have a ton more vials. So if we fill a bunch of these and do a bunch more synthesis, a bunch more compounds coming in, we've got an Orgo class working on them right now, then we can send out even more. And this is just one box. DMARC handed me an empty one yesterday, or a full one yesterday. So we got lots of possibilities. Lastly, I'd like to thank a lot of people. Stefan helped me a lot. I've been doing stuff with him for 3 years, probably, almost like that. DMARC, always giving me the chemicals I need and letting me break glass if I had a bad test, which was pretty cool. Chemistry Summer Researchers, it was a lot of fun this summer. Lawrence Excellent Science Fund for funding me, giving me a job. That was great. And Christian Bell, he's my old roommate. He did this project before me. He actually taught me how to say schistosomiasis. Very important. And lastly, my parents for sending me here and letting me do what I want to do here. So, any questions? Yeah.
So, all the compounds you sent out had nitrogen as a linker to the side chains.
Yep.
And for the ferrocin one, you also proposed doing oxygen. Does oxygen not work real well, or you guys are just on a nitrogen kick? Or?
I don't think the oxygen. So we were purifying one from the summer, and then we started over, and it was just a big batch that we were trying to send out all at the same time. And because so many of the Orgo reactions didn't end up with what we wanted to do a bunch at the same time, so we used the same reaction, and that included just using nitrogen compounds instead. I mean, we could do it with oxygen. That's still an option. We haven't checked that yet, so that's like another step we can take.
So if we're at a bigger university, what methods, what might we do to test whether we actually got the product?
Thank you for asking. There's a bunch of other ways we could test this. We could test this with GCMS if we wanted to. We have one here. But it's a little big for GCMS.
Pretty big for GCMS.
You could also use X-ray crystallography, which you make a crystal of your substance. You shine X-rays through it, and then you literally get a computer image of what your molecule looks like with all the different types on it. So it's pretty impressive. We also don't have that here.
Is there any way to do mass spectrometry and things that aren't volatile?
That aren't volatile?
Yeah.
I mean, there's other mass specs that you can do. There's Multitoph, what else?
Multitoph would be very cool.
Yeah, it's like a mass spec, like if you've seen NCIS, it's a lot like that. It's a lot to get into, but yeah. Lots of other ways to test.
Thank our speaker again.